Hi, I'm Asaf. I'm from Tel Aviv. I'd like to thank Christoph and the organizers for this opportunity to speak here. I'm going to tell you a story about planar maps, random walks, and circle packing. And I thought we would start in the first lecture with just like some introduction to what we're going to do in these 2 weeks and what we're going to prove. And I encourage you to please stop me in the middle of a sentence if you have a question or something is unclear. Don't be shy or hesitant. Everything is supposed to be in my lectures completely elementary and only basic knowledge and probability. So planar maps, random walks, and circle packing, just so we will have the basic terminology that I will use. And again, this is just the first talk will be with this PDF presentation, and we'll discuss the concepts more accurately in the next few hours. So a planar graph or a planar map is a combinatorial object, even though it has some two-dimensional interpretation. It's a graph that you can embed in the plane so that you take each vertex and draw a point on the plane, and each edge is drawn as a continuous curve between the two corresponding vertices so that no two edges intersect. They're allowed to intersect at the vertices, but they're not allowed to cross in the middle of the edges. Here's an example of such a thing. Ooh, this actually works, right? And we use the term triangulation if in this drawing, every face, the face you can think of as a connected component of the plane minus all of the graph that you see. So we say that a graph is a triangulation if each face has exactly 3 edges inside, including the outer face. Okay, we will talk about these things a little bit more later. And a quadrangulation is the same thing, except that each face has 4 edges. This is the basic object that we will be discussing. This is an example of a finite planar graph, and we will be interested in infinite ones. And the other basic thing that appears on in the title of this course is the simple random walk that I assume everybody knows. On a discrete graph, you're at a particular vertex, you choose at random one of your neighbors, you move there, and continue as much as you want. I thought I will start the lectures with something that is not immediately related to these lectures, but just as a sort of motivation, and that is the topic of random planar maps, which I admit to begin with, even though this course will talk a lot about random planar maps, one of the chapters is even say that, I admit from the beginning that I don't know a lot about this topic, except from what I'm going to tell you, and from some other curious facts that I hope to tell you. So when you look at such a map like this, right? And you can consider the space of all triangulations on simple graphs that are planar, and that each face has exactly 3 edges, and there are total n vertices. And if you think about it, you realize that this is a finite space. There are only finite such graphs. And you can think about drawing such a graph at random. This is a very popular topic in contemporary probability. And in fact, there are many ways of doing such a thing. In fact, you can, in the 60s, Tut learned how to count such an object, which is the first thing you can ask yourself. How many of these, what is the size of this space? And the second question that you can ask, which is almost the same, how do I sample from this space uniformly? Right? And these questions are well understood. There are two basic methods, Tut enumeration and these so-called Schaefer bijections. Here's a picture drawn by Nicolas of how a random quadrangulation, a finite one, may look like. Right, so this is it, and you notice that there are some delicacies with the definition. You notice that this face, even though it looks like it has only 3 edges, we count it as 4 edges, because when we walk in this face from left to right or right to left, we count this edge in the inside of the face twice. Right? So there's a little bit of a delicacy of defining these kind of things. And of course, the question that we're interested as probabilists or mathematicians is, as you take n to be large, what can you say about this thing? How does this thing look like? And here's how it looks like, at least a simulation. This weird object that was drawn by Jean-François Marquette. And this is what you do if you draw such a thing and you consider it as a random metric space. You have a metric space on where the points are the vertices, and you consider the graph distance, the shortest path between 2 points. That defines to you a discrete metric space. It turns out that the typical diameter, if you choose 2 vertices at random and you look at the distance between them, it turns out that this distance scales like n to the power 1/4, right? Which is not something that you would immediately guess by any means, but a much more substantial result is that if you scale these distances if you divide all the distances by the n to the 1/4, what you get in the limit in some sort of a limit that has a name, a Gromov-Hausdorff limit, you get some compact random metric space that is homeomorphic to the sphere. And this is big, substantial results due to Le Gall and Mirmont. So notice that even though for each finite n, this random metric space is homeomorphic to the sphere, because you could draw it, right? You could draw it on the sphere, right? We said that we draw it on the plane, but we can always use stereographic projection and draw it on the sphere. But it's not entirely clear that when you take a limit of such a thing, that it would still maintain the property of being homeomorphic to the sphere. And the sphere, I always mean the 2-dimensional sphere and not a higher dimensional sphere. So this is one limiting object that you can take of a random planar map. Another object that somehow works exactly the opposite. So this object captures the global behavior of the map. And we would like to take the point of view that looks at the local behavior of the map. And somehow these two approaches of taking a limit are similar, and you see very similar things happening in them, but they are technically somewhat different, and also perhaps philosophically somehow different. Here's how you take a local limit of a sequence of finite graphs, right? So. And before I tell you what this definition is, and we will come back to it in the second week of this course and see that it is actually a very deep definition, which is, I should say here, due to Oded Shram and Itai Binyamini. What it aims is to capture the local behavior around the typical vertex of a planar map. So here's how you do it. You have, and the definition works for any sequence of finite graphs. It doesn't need to be planar. So here's how it goes. You start with you have a sequence of finite graphs Gn, right? And we would like to say this sequence has a limit, a local limit. And the local limit, the object is a random rooted graph that could and will, in most cases, be infinite, G rho. Right? And how do we obtain it? We choose, in our finite graph Gn, we choose a uniform random vertex, rho n, right? And we look at the neighborhood, right? At the neighborhood of distance r of around rho n. So you look at all the vertices and edges that you can reach from the randomly chosen vertex in paths of distance r, and you map this neighborhood of yours. And now this is a random variable, right? Because you chose the root at random. This is a random variable on a space of graphs, of rooted graphs. Okay, it's not quite clear what is the space. We will discuss this more precisely later. But it is a random variable, and the statement is that if it converges in distribution for any fixed r, it converges to some other random variable, and the random variables are consistent in the sense that they are the r neighborhoods of this random object around this root rho. Right? Then we say that the sequence of finite graphs converges to this graph, to G rho. So let's see some examples of that, because this is a slightly weird concept. Right? Perhaps it will be more natural if I give you a sequence of finite graphs, and for each graph I give you a root. It makes more sense to talk about these these limits, but then you would get a deterministic limit, right? The only point here is that I'm choosing the root at random, and that is supposed to tell me that even if my finite graph has some weird, untypical areas where it looks very bad, or it has some weird decision, has some weird structure, the local limit ignores this thing and only looks at how it looks like from a typical point. Let's look at some examples, and I want to say that even though Gn is can be a deterministic graph, or it can be random in itself, the limit in most cases will be random. So if you start with your finite graph as a path of length n, right, I claim that the limit is the infinite path, the two-sided infinite path. And even here we have to think a little bit. So when you choose, in the path of length n, you choose a random vertex, the probability that it will land within distance r from the edges of this interval is approximately 2r over n, right? And we think about r is fixed and n tending to infinity, so that goes to 0. So it will land somewhere in the middle, and from the middle you see, for any fixed r, you see something that looks like z, right? So this is the meaning of this. Let's skip this example. And let's look at a more clever example where you have a binary tree of height n, right? So it has 2 to the n vertices or leaves. And this is your finite graphs. And perhaps due to the first example, it seems natural to think that the limit would be the infinite binary tree, right? But why is it not the case? Yes, Sebastian? Yeah, the boundary is large, right? When you choose a random vertex, right, you're very in a finite binary tree, you're very unlikely to choose the root, right? Because the most of the vertices are half of the vertices are the leaves, quarter of the vertices are just one level above the leaves, 1/8 of the vertices are 3 levels above the leaves, and so on, right? So you're very likely to choose a vertex at the bottom, and from the bottom, right, the tree looks very different than from the top. Depending if you're, by the way, are you rooting? Is the root at the bottom or is the root at the top? This is one of the arguments that has never been settled in probability. I guess in my pictures the root is at the top and the tree grows downwards. Okay, but I leave you all to choose. So from a leaf, right, the graph looks like this, right? It has one infinite path and these bushes hanging on it, right? So this is definitely not the infinite binary tree, right? For instance, there's only one path leading to infinity, and all other paths find itself into it, right? The binary tree has a bi-infinite path, right, going to infinity for instance, from the root. So this is definitely a different graph. This graph, for instance, is a recurrent graph for the simple random walk, right? The random walk is just an infinite ray on which the random walk is recurrent, and finite bushes hanging on it, so you could project the walk to the one infinite branch, and the walk will be recurrent. So this is the limit, but when I tell you what the limit is, I also need to tell you what is the root. So in this special case, the graph itself is deterministic, but the root is randomly chosen, right? So the root will be a leaf with probability 1/2, will be one above the leaf with probability 1/4, and so on. It copies the distribution from what we had in the finite case. And you may ask, but which vertex is it going to be? Right? There are infinitely many leaves. Which vertex is it? Well, the point is that from the point of view, right, all we care about is, we have a graph, we have a vertex, and we look around us, to see the neighborhood of the distribution, to see the neighborhood of the graph. How does it look like? And from the point of view, when we look at this graph, all the leaves look the same, right? We cannot tell if we are here or here when we're just looking locally at the graph. So in that sense, this is the same object. If I take this graph and root it here, 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 or here, I'm considering it the same object. It's in the same equivalence class. We will define this precisely next week. Okay, so this is so I described to you the limit procedure of finite of a sequence of finite graphs, and we obtain this infinite random rooted graph. And I didn't show you an example, so both here and here, the example that we got was essentially a deterministic graph and perhaps a random root, but there are many examples. You can consider this example and think about it for a little bit. You start with the Erdős-Renyi graph, so this is you start with n vertices and put each edge independently with probability c over n. So this is a random graph, and the definition, if you think about it, the definition of a local limit works very well when you take the finite graphs to be random themselves in some probability space, right? Because we just want this random variable to converge in distribution to this random variable. So if Gn is random in itself, then there's more randomness in here, not just the randomness of the root, but this is still a legitimate, honest-to-God random variable that we will discuss exactly which space that it takes value at. Right, so you can definitely get graphs in the limit which are random themselves, not just the location of the root. Here you can think about it, and you will see that the object that you get is a Galton-Watson tree with a Poisson C branching process. It's almost clear, right? Because on the first step, right, you get your degree is a binomial n minus 1 C over n, which converges to Poisson, and it continues to be like that. And all you have to convince yourself is that you never see cycles in this graph in the first 10 stages or R stages, right? We always think about the radius is fixed but arbitrary, and n going to infinity. So the first question, given what we've seen before, that you can ask yourself, when I choose a random triangulation on n vertices, does it converge in the local sense? So I'm occasionally confusing the word local limit with distributional limit. There's just not a precise nomenclature, and these terms are mixed, but they're synonyms in this course. And it was a pioneering result of Omer Angel and Oded Schramm to show that indeed such an object exists. So there is a limit when you choose a random triangulation on n vertices. It does converge to some infinite triangulation of the plane. So an infinite triangulation of the plane just means that this graph can be drawn in the plane, right? So that so the union of all the faces and the edges, right, is exactly the plane. So I think about it as a partition of the plane into shapes, right, that have exactly 3 edges. We'll discuss this object a little bit more. But what it means is that it doesn't degenerate to some weird limit that is a point or something like that. But this local limit really exists, and it is commonly known as the uniform infinite planar triangulation. So this is the local. This infinite graph represents how random planar maps look locally. Here's a picture of it drawn by Nicolas in the case that the graph is a quadrangulation. So somehow with quadrangulation, there are like very neat methods of sampling it. And here's a drawing of it that is actually drawn not very good. But here is a picture that I like more, where because this picture emphasizes the point. So this is the root, that we're not just getting a graph, we're always getting a rooted graph. So we have a graph, we think of ourselves as the root, and we look forward and consider our neighborhoods. And these are the events that we are allowed to determine. How does the neighborhood look at radius 10, radius 100, and of course all the events that are generated by this thing. So this is a random planar graph, an infinite one, right? There's some weird probability space that it's drawn from. So it's natural to ask, what are its basic properties? We know another infinite graph, and that's Z2, the square lattice or the triangular lattice. Question, yes?
Yes. Do you have a simple way to construct?
Yes. And here, the fact that there is a picture that is actually drawn suggests that there are very nice algorithmic ways of sampling such a thing. We will not discuss these at this course, I'm afraid. Okay. Any other questions? Right? Please feel free. It's a seminary, but you won't be. I won't hit you if you ask a bad question. perhaps. So we know another graph, another planar infinite graph that we are very familiar with is Z2, the square lattice or the triangular lattice. There are all sorts of these graphs, and we may ask ourselves, you know, what can we compare the two graphs? And indeed, they are similar in some rough sense. One thing that we know about this UIPT that was proved by Omer Angel and Oded Shram is that it's one-ended, and that means that if you remove any finite set of vertices, then what you get outside contains only one infinite component. Right? So the same is true for Z2, right? You remove some ball in the middle, you still have only one infinite component surrounding it. It's not true, for instance, for Z, right? You remove something, you get two infinite components, right? Z is two-ended, Z2 and the UIPT are one-ended. Another property, for instance, is that the critical percolation probability on it is also 1/2, just like on Z2. Let's not discuss it, but the truth is these are very non-similar graphs. The UIPT is a very fractal graph, and it because it's drawn from some sort of a random distribution. The first thing that we understand that is a basic difference between Z2 and the UIPT is that the degrees are unbounded. Right? When you have a random planar map on n vertices, there's no reason that, you know, with high probability, all the degrees will be smaller or equal to 11. Right? So obviously there's some positive fraction, even without knowing how to draw such a thing, you can imagine that you can find these arguments or find enough planar maps that have a positive fraction of their vertices to have degree 11. So because of that, you cannot expect that in the limit, the degree will be bounded by some finite number, and it's indeed unbounded. Question?
What is the tail of the degree?
Yes, very good question. That was my next sentence. But it is true that the tail of the degree decays exponentially. So if you draw from a random planar graph, if you draw a random vertex, the probability that the degree is bigger than k decays exponentially in k. And this is indeed a very useful property that we will discuss. So this is that. But here is perhaps the most major difference from this graph UIPT and Z2 is the fact that it has the completely different volume growth. So if you look at a ball in the graph distance of radius r, all the vertices that you can get from the root in paths of length r, this set has roughly r to the 4 vertices and not r square like we used to. So it's a graph that looks very fractal in the sense that it has this. If this is the root, right? It has all, you know, this parts that go to infinity, and it has all these finite bushes on it that become larger and larger, and in fact occupy most of the mass, right? And so on. So this is just a schematic drawing. It's hard to see, but this is a graph that looks very different from Z2, and because of that, the random walk on it behaves very differently from Z2, in the sense that when the random walks on this graph, unlike Z2 where it diffuses the Brownian motion, here it spends a lot of its time on these finite bushes before proceeding to infinity. But what we will see in this course is that in some sense, even though this picture is suggestive in some way, in some sense there is a way to draw the graph in the right way so that the random walk does behave in a nice way. But the first thing we can ask about the random walk on this graph, of course, is it recurrent or transient? Right? This is we know that. I hope everybody knows that on Z2 the random walk is recurrent. If not, you will see a proof of this fact in this course today or tomorrow. And indeed, it's when we think about this question, it becomes the question of unbounded. The issue of unbounded degree becomes pertinent, becomes very important. In the sense that there is a very general theorem due to Oded Shram and Itai Binyamini, and it is in the same very citable paper where they define this concept of a local limit of finite graphs, in which they state the following. If you take the local limit, distributional limit of finite planar graphs that have bounded degree, right? So this is, I give you a sequence of planar graphs with bounded degree, and I tell you that they converge, or perhaps you take some subsequence of it that converges, then the limit will almost surely be recurrent. So this is a strange statement in the sense that notice that even if I start with completely deterministic sequence, the limit is still random, so I cannot argue, so I have to add the words almost surely here, right? So it is almost surely recurrent. So what the statement says, for example, who can give me an example of a transient planar graph? Just so we'll be on the same page. Sorry? A tree, right? The binary tree is transient, right? When you look at the distance from the root, it behaves like a simple random walk that has a drift towards infinity. The probability of going down is 2/3, going up is 1/3, so you will be swallowed in the depth of the tree. It's obviously planar, because here is a drawing of it, right? Right? So what the statement says that if I start with planar graphs, for instance, one of the corollaries of the statement, if I start with a sequence of planar graphs, I can never obtain the binary tree as a limit, right? Or the three regular tree as a limit. You may ask yourself, can I get the 3 regular tree from some as a local limit of some sequence of graphs? Yes. Right? I'll leave you to think about why. And the reason, or I'll tell you the answer, or Sebastian will tell the answer. You said yes.
Yeah, there is a free group in SL2Z, and we can.
Sorry?
There is a free group in SL2Z, and we can take congruent subgroups.
Okay, that works, but perhaps a simpler.
Random graphs.
Yeah, you could take. So, in fact, why would you get? All you need to find is a sequence of finite graphs on n vertices, where from every, such that the girth, the size, for each vertex, the size of the largest cycle, right, goes to infinity. So it's a graph that locally looks like a tree. And it's not immediately clear that such things exist, but you can make it. And the best example is to choose a random 3 regular graph. So this is something that you can draw. And it turns out that this graph does not have very short cycles from almost all of the vertices. So this will be a concrete example. What Sebastian said was an even better example where you won't have short cycles from every particular vertex, and it's a deterministic graph. So such graphs with large girth that are 3 regular exists. By the way, it's still an open question to determine how large the girth can be in any 3 regular graph on n vertices. How big can it be? What is it? So it can only be some logarithm of log of n, but the question is what is the right constant there? But all we care in this case is that you have some function of n going to infinity such that the girth, the size of the shortest cycle, sorry, not the largest cycle, right, goes to infinity, and that will give you the 3 regular or the infinite binary tree. So if you start with, however, if you start with planar, if your input is a planar graph, then you never get something that could look like the tree. It will always be a recurrent graph. And examples that we saw are Z or Z2, right? If you start with n by n boxes and take the limit, you get Z2. We also saw the example of the canopy tree, which we said was recurrent. And indeed, this theorem only works with the bounded degree assumption. Here's an example that is a little bit hard to see. So you start with a graph that looks like the canopy tree, but then you add multiple edges. So and here the leaves, all the edges touching the leaves have the number 1, the label 1 written on them. Above them you have the number 2, meaning that there will be 2 parallel edges there. And above them you have 4 edges, right? And you can convince yourself that this is a limit of a sequence of finite planar maps, and observe to yourself that because the numbers here are 1, 2, 4, 8, 16, and so forth, the random walker will actually be transient, right? When you project the walker to the one infinite path, it will have bias, a drift towards going towards infinity, and not unbiased. So you indeed need this this bounded degree assumption. So this theorem does not apply to the graph that we discussed, the UIPT. But indeed, as Sebastian said, this graph, the UIPT, has an exponential tail on the degree. And one of the goals of these lectures is to show you a complete proof of the following theorem due to Ori Gurel-Gurevich and myself. If you have a local limit of finite planar graphs, but this time the degree may be unbounded, but you have some distributional knowledge about you know something about the distribution of the degree of the root, in particular you know that it has an exponential tail, then it implies that the graph is recurrent. Right? So this is what we will prove, and this is interesting because for the random graphs that we discussed, it is already known, and it's not very difficult to prove, that these indeed have exponential tail on the degrees. This is not something we proved, that this was already known much before. So this is what I mean when I tell you I don't know much about random planar maps, because what we will prove is a general statement that does not use the intricate delicacies of random planar maps and their structure, just will prove a general result that works under just this assumption, and I will try to convince you that it is true. Indeed, it is sharp in the sense that anything worse than exponential or more than exponential does not work. Any questions about this random planar maps business? So the proofs of all of this business work. We use this the third word or sentence in the lecture notes, and that is the circle packing theorem. So this is why I like this area, because the circle packing theorem is a theorem. It's a geometric combinatorial theorem. It doesn't seem to have anything to do with probability. It is very nice in my opinion, because it produces all sorts of very nice pictures. And you know, who cares about the math when you can show very nice pictures? And this is the reason I chose to give a presentation in the first class, because I'll show you some really nice pictures that I'm even proud to say that some of them I have, with my co-authors, generated myself. So it's not only a completely theoretical theorem, but it also you can calculate things. So what is the circle packing theorem? Let me first describe to you what it is. It's a very easy theorem to state. Question? No? It's a very easy theorem to state. You have a finite, simple planar graph. Here it is, for instance, with points and edges. And of course, it is clear to us that there are many ways of drawing one particular graph, right? I could take this edge, move it a little bit here, deform it a little bit there, and I get, another mapping, another representation, another drawing. We'll use the word drawing of the same graph. But the question that we ask ourselves is there a canonical way to draw a planar graph? And it turns out that there's actually a lot of theory in the combinatorial geometry communities about how to draw graphs. The method of drawing that we're interested in, that is widely used and is very popular, is the circle packing theorem, which states that any simple planar graph is a tangency graph of a circle packing. So here's a circle packing of the same graph. What is a circle packing? So it's a very simple thing. It's just a set of circles in the plane, right, with disjoint interiors. Okay, so they are disjoint circles, except for their boundaries that may be tangent or not tangent. And if you have such a drawing, right, you can consider a graph on it, right? The vertices of the graph are the circles themselves, and if two circles are tangent, you put an edge. So in this drawing, it's a little bit hard to see, I drew edges between every two circles that are tangent to each other. And if you have such a drawing, right, if you consider this drawing, you see that it's a drawing of a planar graph, right? Because you cannot have two edges intersect this way. Right? That's easy to convince yourself. But the true power of the circle packing theorem is that the converse statement holds. If I start with any planar graph, and I just know that there is some weird drawing, right, it can always be represented as a circle packing. I can always find circles and put them in these in this weird locations and sizes, so that the graph, the tangency graph that I obtain, right, the tangency graph is just what I described. Circles, two circles are an edge if and only if they are tangent. The tangency graph is the original graph that I started. So it gives you, you are given a combinatorial information. Here's a graph, a set of vertices and edges, and a bit that tells you this graph can be drawn in the plane. And now you have an algorithm or a theorem that tells you, I could draw it as a circle packing, and here is the drawing. We will prove this theorem after the French-Belgium match that we'll all be relaxed. And it turns out that there is even a uniqueness statement in this theorem. Obviously, just like this theorem, we cannot have uniqueness, right? You can even look at this picture and look at this circle, for instance. I can push it a little bit higher and move this circle a little bit to the left, this circle a little bit to the right, and the picture will not be unique, right? And even more than that, I could reflect this whole picture, right? And even more than that, I can take any mapping from the plane to the plane that sends circles to circles, any continuous mapping such as that, like a Möbius map, and I will get even another different circle packing, right? I can even translate, right? It's not the same circle. But it turns out that if your graph is a triangulation, then this drawing is unique up to the only mappings that it could be unique to, mappings that send circles to circles, and these are Möbius transformations and reflections, or all their compositions. Okay, so these are sometimes called generalized Möbius transformations. But the theorem is stated for a finite graph, right? And it's indeed a theorem that was proved. It has a very nice history that you can read in the introduction to the notes. It was discovered by Kebe, the complex analyst, in 1936, but then was somehow forgotten because of the war and because he wrote in German. And it was rediscovered by Thurston in 1985, and somehow he found it as a corollary to a result due to Andreev. And only a few years later, when this topic became very popular in complex analysis, not in probability, did they realize that it was Kebe who first discovered this theorem, Paul Kebe. And at this point, we still don't know what this theory has to do with probability, but this is the main point of this course. I will try to convince you that this theorem is in fact a theorem in probability. And it will tell us a lot about the behavior of the random walk on the graph and all sorts of other random processes of the graph. But for that, we need to understand how this theory extends to infinite graphs. And indeed, you can first ask, when I have an infinite planar graph, like a Z2 or any other graph, can you represent it as a circle packing? And the answer is always yes. Because you can always take finite chunks of the infinite graph, just take some root and consider balls in the graph distance that become larger and larger, draw them according to the previous theorem about finite graphs, and then take some sort of a limit. And you have to argue that this limit exists. We will perform this argument. So you always have limits. However, depending on the way you approximate your infinite graph, by the way you choose the limit, you may get very different looking packings that are not Möbius equivalent. Here's a picture. Where is the picture? Oh, here's a picture. So if you look at this is a picture of two infinite circle packings, right? You have infinitely many circles, but they represent the same graph. This is the 7 regular hyperbolic tessellation. So if you believe me, which I encourage you never to do, If you look at the neighborhoods of this graph, you will see that it's combinatorially, this is the same graph, drawn in two ways. And these ways are obviously not Möbius equivalent because a Möbius map will never move a circle into a square. And it turns out that I can put here any shape that I want and pack this graph in it so that it converges to the boundary of the shape. So there's no rigidity in this sense. If I have an infinite graph, I may obtain very different packings. However, there's a certain notion of a type of a graph, and this is a very important notion for us because this is something that is maintained, that the type of the packing. For instance, here you could say, the type of the packing is the fact that, okay, what is common to these two pictures is that it is bounded, right? The circle packing, the entire picture is bounded in some bounded domain, right? And of course, we have pictures that you can imagine of a circle packing of an infinite graph, just like the triangular lattice, right? Which occupy all the space that we have. So this is a particular notion of type. And the point is that this type of the circle packing encodes in it a lot of important probabilistic information, such as, for instance, the recurrence or transients, all sorts of notions of harmonic function, the speed of the random walk, the connectivity or disconnectivity of the uniform spanning force. So there's a lot of probability encoded in this thing that we will discuss in this course. And here's the canonical example. So let's just state one important theorem that we will prove in this class regarding infinite circle packings, and this is the Schramm theorem. Let's just go, just so we'll have, in case you haven't listened, let's just repeat the definitions very quickly. A circle packing is a set of circles in the plane. They have disjoint interiors. The tangency graph is indeed the graph that you obtain by considering every circle as a vertex, and two circles are considered an edge if and only if they are tangent to each other. An accumulation point, now I'm thinking about the world where my set of circles is an infinite countable set, so I may have accumulation point. It's a point in the plane which gets closer to infinitely many circles, right? So it's a point such that every neighborhood of it intersects infinitely many circles. And when we discuss triangulations, we discuss this notion of the carrier of the circle packing. And before saying what it is, I'll just tell you that the carrier here is the square, including what's inside, and the carrier here is the disk. So it's the domain in R2 in which the things are drawn, and the way we obtain it is we go over all the faces, right? And we take the union of all the circles and that little triangular space between them, right? So the carrier is going to be the union. I go over every face of the graph. So here is a face, three mutually tangent circles. I take their union, including the boundary, the closed circles, and also this space that is called in English the interstice, but I never heard this word before I looked into this theory, so I don't expect anyone to know this word. It's a word, apparently, the interstice. I take the union of all this, and this is the carrier of the circle packing. And you can convince yourself that if I look at the set of accumulation points, then this is exactly the topological boundary of the carrier. So just like here, the boundary of the square, each point on it, each neighborhood intersects infinitely many of the circles, while a point inside the square intersects only finitely many circles. Right? So this is the carrier of a circle packing. So here is this nice pictures due to Ken Stephenson, and if you Google this name, you will find a beautiful book with some beautiful pictures that are all online of circle packings, and a wonderful story about the connection of the circle packing theorem to various issues in complex analysis, in particular the Riemann mapping theorem that we will not really address in this course. But here you see a graph that is circle packed inside the unit disk, and outside you see a graph that is circle packed inside all of R2. The carrier is all of R2. Here the carrier is the unit disk. And here, this is a finite graph that we can always circle pack on the sphere, on the two-dimensional sphere. and that it will be its carrier. We usually will pack things in the plane and not in the sphere, so you don't have to worry about that. So here's the carrier again. And here is the main, the first theorem that due to Oded Schramm and I forget his co-author's first name, never mind, but I apologize. Not only, so this is an interesting theorem. No probability here yet. So this states that if you have a graph that you can circle pack inside the unit disk, you cannot circle pack it so that the carrier is all of the plane, and vice versa. Right? If I have a graph that is circle packed such that the carrier is all of the plane, you cannot pack it inside the unit disk. As an example here, so the statement suggests that the triangular lattice here cannot be packed inside the unit disk. This is pretty remarkable because it seems completely obvious. Right? Obviously, how would you draw circles here so that they will all fit nicely inside, inside the unit disk, or perhaps inside some bounded shape? And the same thing here. It looks completely obvious. But it is true you cannot do it. And what is the reason? The reason is that this graph is a recurrent graph for the simple random walk, and this graph is a transient graph for the simple random walk. And this is essentially what they proved. Because transience and recurrence of the simple random walk is a combinatorial information, right? It's just based on the combinatorics of the graph. That does not change when you have different circle packings. So what they proved is that every recurrent graph can only be drawn like this, and every transient graph can only be drawn like this. So obviously, you cannot draw the same graph in the two ways. And here is the statement. When your graph, and I should add for this theorem to hold, and it's very important, this theorem, or this reason that I suggested, only works when the graph has a bounded degree. So if you start with a bounded degree triangulation of the plane, or some infinite triangulation, that's all we need to think of right now, then you could draw it's CP parabolic, meaning that CP parabolic is the term that we use to say that you could draw it so that the carrier is all of the plane. Right? Can be circle packed in the plane, that is parabolic, or in the unit disk, that's what we call hyperbolic. Right? So you can pack it in the plane if and only if the random walk on it is recurrent. A corollary, of course, that if you have such a graph, you cannot pack it in the disk because otherwise it will not be recurrent. Not only that, when you have a transient graph, right? If you have a hyperbolic, right? So if you can draw it, right? Because there is an if and only if here, it suggests that if you can draw it, it states, not suggests. The claim is that if you can draw it inside the unit disk, then it has to be transient. And not only is it transient, when you look at the random walker, the location of the random walker on the circle packing, it converges to a point on the boundary of the circle, which is not a trivial statement, right? Because it can spiral somehow next to the boundary and not converge to any point. But the point is, but it does converge. And the exit measure, when you look at the measure on the boundary, the exit measure is non-atomic and has full measure. It's not Lebesgue measure in any way. It's some weird measure that actually very little is known about it. But this statement, just the fact that it converges, implies in some sense that there are non-constant bounded harmonic functions on this graph. Let's not go into this issue, and let's discuss. So we have here. So this Schramm theorem gives us a dichotomy, right? It tells us the class of bounded degree triangulations, infinite ones, can be split exactly into two. You have the graphs that are recurrent. Right? The random walk on them is recurrent, and in this case, you can always draw them in the plane. Of course, they're recurrent, so you don't have any bounded harmonic functions. Or they are transient, and in this case, you can always draw them in the unit disk. And it turns out that you can draw them in a unique way in the unit disk, up to Möbius transformations of the unit disk to itself. and this graph is transient. So obviously, once you see this theorem from 1995, it makes the way that we will use it is to prove that something is recurrent. We'll try to show that the drawing occupies the entire plane. Right? To prove that something is transient, we'll try to pack it. We'll try to argue to study the circle packing theorem to show that you can pack it inside the unit disk, and vice versa. Perhaps we'll somehow know that it can be packed inside the unit disk, and we'll conclude transience and all other properties that we will see. And we will in this course we will see that this interaction between the circle packing theorem, which is a way to draw the graph, and the geometry and the combinatorics of the graph itself, such as the behavior of the random walk, they affect each other in both ways. So if we want to study the random walk, we can figure out how the graph is drawn by the circle packing theorem, but also the other way around. If we want to show some properties of the circle packing, we will study the random walk on the graph and see some properties of it and discover that they enforce the graph to be drawn by the circle packing in a certain way. So these are very intimately connected notions of the graph that I hope that I will convince you in this course that they interact very well with each other. Never mind this. Here are some more fun pictures, just to give you an intuition to what's going on here. So here, the picture is not drawn very. The circles in white, as you can see, all the degrees except for the boundary, they have degree 6. It isn't. So what I did here was I took the the triangular lattice, right? Just the usual triangular lattice drawn in the plane by circle packing by the picture that we saw earlier, the circles in red. I took half of it, and to the other half, I put on the bottom half the triangular lattice, and on the top half I put the seven regular hyperbolic tessellation. Right, only at the half of it. And this is a combinatorial gluing, right? I just took the one graph, infinite graph at the bottom, the transient graph at the top. So obviously this is a transient graph, right? You have a recurrent graph at the bottom, so you will return to the top graph like infinitely often, and then in one time you will be sucked up into infinity, right? It just takes one time to do that. And I took this graph and circle packed it, and this is the way that it is drawn. Right, all of the recurrent graph is accumulated to a single point on the boundary. It's hard to see here, but there's just a single point that all of the circles. So this line here goes into a one particular point, and the transient graph captures all of the boundary of the unit disk except for one point. And this is. From this we understand, okay, so it's a larger graph, right? It's transient. The random walk escapes to the boundary, but it cannot escape inside the white circles, because this is the part that is recurrent. So the boundary contains only one point. So when we have the feeling, if I have Brownian motion on this disk, the probability that it exits in one single point is 0, right? And this notion is actually correct in some sense, even though the exit measure, as I told you, is not Lebesgue. It's not absolutely continuous to Lebesgue. It's a very strange singular measure, but there are many connotations and analogies with Brownian motion, and in fact, there's even a precise statement or a semi-precise statement that you can say that the random walk on the circle packing is a quasi-conformal image of Brownian motion. And if you know what it means, then great. If not, don't worry about it. So this is just a picture to illustrate how some probabilistic properties of the graph, even in the transient case, are manifested in the circle packing. Here's another graph that the purpose of this picture is to show you that the graph, even though from many, many points could look like a very recurrent graph, it could still be a transient graph, and circle packing it shows it. So this is a graph in which you have an exponentially small density of vertices of degree 7, and everything and these are the gray ones, and everything in white, which occupies almost all of the graph, is a it has degree 6 and looks like the triangular lattice, in the long run, this graph is a transient graph. And the way to figure it out is simply to draw it and to see that the lengths go to 0 and that they are summable. So this is one particular example. This is an example of something I'm not sure we'll have time to discuss. This is an example of the circle packing of a random hyperbolic triangulation, random transient triangulations with unbounded degree. And here is it's a nice picture of the circle packing, and this is the reason that I put it on. So we started talking about the UIPT, the random planar maps, and the first thing that I told you is a big difference is the fact that the degrees are unbounded. Right? So this whole theory that I just told you here, this theory, only works when the degree is bounded. And here is an example to show you that in all of this theory, without bounded degree, there is no theory. You cannot hope to have any statement that is correct. So for instance, one statement is that if you have a circle packing that covers the whole plane, right, that is drawn on the entire plane, then the random walk is recurrent. Here's an example without the bounded degree in which this statement fails. So it'll be hard to draw it. So you start with the triangular lattice. Imagine that it is drawn on the entire plane. And now I'm going to start adding circles to it to make it a transient graph. So here's what I do. I'll add one circle here and then another circle here so that it touches all the 3 circles. And then here I'll add 2 circles. You see one big one and one small one here. There's always space to put more circles. Here I'll put 4 circles here and 4 circles here. Here I'll put 8 circles here and 8 more circles here. And you will go on and on. The random walk does not know what the size of the circles are, right? It just chooses a random neighbor, goes there. So when you are here, you will have more circles to your right than to your left, right? So you will be more tempted to go to your right. And when you're on one of these very small circles, you're essentially a martingale. Going left and right has equal probability for you. But when you are here, you will have a drift to your right. So this is very similar to when you take Z2 and you choose one infinite ray that goes to infinity, and you put a bias there to go more and more right. And you can convince yourself the random walker will hit, because the walk on Z2 is recurrent, it's going to hit this infinite line infinitely often and will accumulate this drift that you put on it. And eventually, it will go to the right, and hence it will be transient. So this is an example where to show you that you without bounded degree, you cannot do nothing in this. And in fact, for any statement here, except one statement, for any statement here, there's a counterexample unless you assume bounded degree. Well, there's one statement that is true without the assumption of bounded degree, but that's not enough to create the dichotomy. So there's no hope. To have such a theory without the bounded degree. But there is a hope to produce a theory when your underlying graphs are random themselves, just like the UIPT. And this will be the goal of this class, to show you in the first week the classical theory, how you prove such things in the bounded degree case, and in the second week how you extend this theory when your underlying graphs are random. And we have to discuss what sort of randomness is needed to make the circle packing theory work. So the plan of what we will do, just to give you a slight outline, is we will study, the first thing that we will study is a very basic classical probability topic, electric networks and random walks. By the way, who have seen here electric networks and can, know what it is? Okay, some of you. Okay, so if you'll be bored, feel free to go to YouTube. This should take the half an hour of this class and the next class. After which we will see the circle packing theorem and produce its proof. The goal is in this class is so that the class is supposed to be self-contained. I will show you the proof of everything from the beginning, including this classical theorem from 1936. We will prove parts of the Heshram theorem that I discussed to you about infinite packings, recurrence and transience, the dichotomy. And after that, we'll discuss how to prove recurrence for random planar maps. And if we'll have time, I will tell you a story about, just to convince you that the theory of circle packing is useful for probability, not just to study random walk, but for other probabilistic models, such as the uniform spanning forest on planar graphs. And I want to make one comment about the notes. So the notes, which have a typo in the very first page of it. It's not the circle theorem, the front page. It's the circle packing theorem. I did not design this part, but the notes contain full proofs of everything that I will say in this class, and unfortunately, I will not have time to show you absolutely everything. So there will be parts of this, parts of the lectures where I will tell you something of the form. And here, if you spend half an hour with the notes, you will see a neat proof of this and that. And here is a sketch. I hope you understand. And I made a sincere effort that everything will be understandable and readable in the proofs, in the notes. They are, firstly, they are incomplete in the sense that there's a chapter missing, chapter 7. About the uniform spanning forest is not written. It's at the end of the course, and I hope we'll get there, but take that in mind. And thirdly, it is a preliminary draft, so there are many mistakes. There are some even well-hidden mathematical mistakes in it, and of course, many typos and other kind of errors. And I encourage you, please, if you see any mistake, come, and even if it's a small typo, make a list of it and send it to me, or come and talk to me about it. I'll be very happy, and if I'm in a good mood, I will buy you a beer to show my gratitude. Okay, so let's start discussing the electric network part of this course. Let's see if I guess I can. All right. So again, I encourage you, please stop me if there's, I know it's a big classroom and you guys seem to be very, very shy, but please stop me if you have any questions or if I'm saying something that is not clear. And of course, when I make a mistake on the board, I'm Israeli, so I can promise you that I will never be insulted by anything that you have to say, or if you cut me in the middle. So the topic that we will briefly discuss today and tomorrow is electric networks. All of it is contained in the second chapter of the notes. The first chapter, if you are bored at night and you want to read a nice story about circle packings and all of the things that I haven't told you, the first chapter is a fun bedtime reading. What is a network? So a network is just a graph. A network is a finite connected graph with non-negative edge weights. Right? So we put on each edge a non-negative number, or even a positive number with, let's say, positive edge weights. Which I usually denote and call the conductances of an edge, the electric conductance of an edge. So this is just, if the graph is G, E of G is the set of edges, CE is just the conductance of the edge. And these are positive numbers, and their reciprocals are called the edge resistances on this graph. So one RE is defined to be 1 over CE, and we call it the edge resistance. And again, so we have a finite graph. We have edge resistances on it. We have 2 points, and we want to think about this graph as an electric network. So this is really the same direct electricity that some of us learned in high school, where we think about this as an electric network. We put a battery, the minus of the battery at one vertex, the plus at the other vertex, and we let the current flow from minus to plus, or from plus to minus, depending on which communist country you live at. And we would like to study this as a 1 unit. So it turns out this theory tells you that there is each finite network you can replace by a network with a single edge, right? And this edge will have a certain resistance that determines, that you look at it as a circuit, it's as if you can replace the circuit by one edge that has a particular resistance and put it in your much larger electric network. So this is the theory. How do we reduce any such network to a network with one edge that has a certain resistance on it that we will call the effective resistance? So there are many ways to mathematically teach this. We can start with what is the axioms of electricity that we want to hold, and then decide what is and figure out what a voltage is and what is the exact current. But I'll do it the other way around. I'll define to you what a voltage is, and as some of you probably know, a voltage is a harmonic function, except for perhaps a few points. So let's define another thing. So a function h from G. So G will always be my graph, finite connected graph G, from G to R, right? It's a real valued function, is harmonic at a vertex, harmonic at x, if the value of the function at x is simply the average according to the weights of the values of the function on the neighbors of x. So meaning if h of x is the sum over all the vertices y that are y is a neighbor of x, right? This is my notation for y and x being adjacent in the graph G, of hy with the weight c xy, which is xy is the edge, so this is CE, when I divide by the normalizing factor, which I will call pi of x, right? And pi of x, for this to be, I think about it as a probability measure, I need pi of x to be the sum over y of cxy. So pi of x is the stationary distribution, or a stationary measure on the on the vertices, is just the sum over y neighbor of x of cxy, the amount of electric conductance coming out of a vertex, right? So this is something that we are very familiar with, and all of this I assume that you are familiar with, but if not, then it's okay. A voltage, so a voltage, let's just say what it is. A voltage, so before I say a voltage, is from now on we distinguish, let A and Z be 2 vertices. So from now on I will call A and Z the source and the sink of the of my electric network, and the voltage is just a function that is harmonic on every point except for A and G. Right? So a voltage is harmonic, is a function. What do I use? I use the word V, but let's still use H. Is a real valued function from the vertices of your graph to the real numbers that is harmonic at every vertex except the 2 points, which is harmonic on V minus AZ. Okay? And on AZ it receives some values. So the first thing that we want to argue is that once I know the boundary values, then the voltage is uniquely determined, right? And for this we need to state the simple claim if let H be a harmonic, so if I start with a function that is a harmonic on all the vertices of the graph, of the network, what could this function be? Let H be harmonic on G. So by this I mean that it's harmonic on every vertex of G. What will be the statement? Right, it has to be the constant function. The constant function with any constant is obviously harmonic, right? The value at each vertex is the average. And it turns out that if it's because it's a finite graph, if it's harmonic everywhere, then it's a constant function. Then H is constant. What is the reason? The maximum principle, right? If it was not constant, right? So proof, if not, or let's just say without the proof by contradiction because it's just bad style. So let the m be the maximum of the function of f of x and g, right? And let's say f of x0 is m. Right? So if I look at the maximal value of this function, and now it's a finite graph, and I look at all, and I know that the value at this vertex where the function has the maximum value is the average of the neighbors according to with some weights. So if one of these neighbors would have a value smaller than the maximum, then it cannot be an average, right? Because they're all smaller or equal to this number m, right? So all the values of the neighbors also have to be to have the value m, right? Otherwise, harmonicity is does not hold, right? F of x0. So hence, by harmonicity at x0, all values of neighbors of x0 must be m as well, right? And now we continue, right? From each neighbor, apply the same argument. So we learned that all the neighbors of x0 have to have value m. All the neighbors of the neighbors of x0 also have to have this value m. And all the neighbors of the neighbors of the neighbors, and so on. And because we started with a connected graph, the electric network is always connected, we obtained that all the values of the function must be m. We continue by considering the neighbors of x0. The neighbors of x0, and so forth, right? And obtain that f equals m, right? Where did we use the finiteness of the graph? Sorry? Right, I took the maximum, right? If it was an infinite graph, this maximum is not necessarily attained. And indeed, when you have a harmonic function on an infinite graph, this is such a thing that exists. You can have a local maximum, you cannot have a global maximum that is attained. Okay, so this is the first basic property, and what it tells you is that if you have a voltage, right, and it's if you have two voltages with the same values on the two boundary vertices A and Z, then they have to be the same, right? Let's prove it. Oh, oops. Well, let's just first state it. So the claim, right? If H is a voltage with h of a equals h of z equals 0, then h has to equal 0 everywhere. Yes?
Why do we define h on G? Why not just
So we define, we just say that a function that for every vertex returns, the definition is harmonic at x. So you mean G and not V of G? Will this be better? This is what I meant. Okay. Defined on the vertices, yes. Not on the edges, sorry. And if this was unclear, the function gives every vertex a number, not the edges. Sorry about that. So usually this is just the way to write it. So if you have a voltage that receives 0 on both sides, it has to be 0 everywhere. Why is that? Right, the same reason, right? If you had a value that is bigger than 0, right, then all its neighbors have to be 0, right? And all of its, bigger than 0, so say 5, right? It's the value 5, then all its neighbors have to be 5, and so forth. All its neighbors have to be 5 until you reach the 0 vertices, so you cannot, so this is a contradiction. So the function cannot receive positive values, and by the same thing, it cannot receive negative values, right? So this is an explanation, right? So this is the same argument. And so we learn, so the corollary, right, if H1 and H2 are voltages such that H1 of A equals H2 of A, right, and H1 of Z equals H2 of Z, right, then if they're equal on the boundary, they have to be equal everywhere inside. Then H1 equals H2, right? And the reason is you simply subtract the two of them, right? And you get a voltage that receives 0 in the beginning and 0 at the end. And for this, you have to notice indeed that if you have two harmonic functions at a vertex x, right, h and g, h satisfies this and g satisfies the same thing. If you add them, right, the harmonicity is a linear constraint. So if you add them, you have the same constraint because these are the same coefficients with h plus g. So adding or subtracting two functions that are harmonic at a vertex is also going to be harmonic at the vertex, right? So we discovered that if I have an electric network with 2 points, right? If I have a voltage is a function that has a harmonic inside except the 2 points. If I give you two of them, so the voltages have to be unique. If I tell you the values, there can only be at most one function that is harmonic inside and receives the two values on the outside. And I claim that such a function has to exist. Right? There is a function for any two values on the boundary, on A and Z, there is a function that is harmonic on the inside. What is the reason for that? Yes?
There is uniqueness and there are as many equations as...
Sorry? Yes, exactly. So I have to, for each vertex, I have to, right, I have this, each vertex has this equation that it has to fill, right? I have to give each vertex a number and it has to satisfy this, right? So, and I know the numbers at the boundary, so the number of equations that I have inside is n minus 2, right? N is the number of vertices on the graph. These are all linear homogeneous equations, right? Actually, they're not homogeneous, right? Because if you're a neighbor of A and Z, right, then here you have a constant and not a variable written. So you have n minus 2 variables, right? All the numbers that you have to put on the vertices, and you have n minus 2 equations, right? Because every vertex defines an equation. But this shows you that this linear system that you get, this matrix n by n minus 2 by n minus 2 matrix is actually invertible, so it has to have a solution. So this is one proof of existence, but I prefer to provide you a proof that is more probabilistic. What will that be, by the way? What will be the value of the function at a particular point x? Right, it has a probabilistic interpretation. And here is the And here it is. And this will be very useful for us. And this is in some sense the correct way to think about harmonic functions. So when we have a network, we have a random walk defined on this network, right? So the definition, the random walk on the network, right, is the Markov chain with transition probabilities. So the state space is the vertices of the with state space V, right, and transition probabilities. Right, so I just define the probability to move from vertex x to vertex y to be proportional to cxy, to the conductance on the edge. If the conductance is large, I'm more inclined to go on this edge. So this will be cxy divided by pi x, the sum of the cxy's over y. Right, so this is an honest-to-God Markov chain. When all the cxy are the same number, we just get the simple random walk on the graph. Right, so sometimes we call these, if we put all of the cxy as 1, we just say that this is a graph with unit resistances. Right? Unit means 1. So what is the way to, once we have this process, what is the way to generate the harmonic function corresponding to a vertex? So let me tell you what it is. Okay, this was not meant to be. I'll just leave it here. So the claim is, given values for a z, there exists, and it is unique by the previous statement, a voltage h with these values on a and z. Right, and the proof, we already said one proof using linear algebra. The other proof is the following, right? For any x that is not in a and z, right? I just define h of x to be the probability, right? So once I have this Markov chain, I have a sequence of random variable xn, which are the random walk. According to these transition probabilities, an instance of it. Right? So this is just the probability that the random walk xn visits A before Z. Right? And sometimes we write, and we will use, right, in other words, or h of x, the standard notation for that is to write p of x here, which meaning the random walk starts at the vertex x. It visits A, so tau A is smaller than tau z, when tau of any vertex is the first hitting time of this vertex. So this is a stopping time once you hit the vertex. So this is stopping time at A. Right. So this function, let's consider this function. This function is obviously harmonic, right? Because, let's even call it, h tilde, not this h. Right? This function is harmonic, right? Because when I look at this thing, right, the probability, let's look at this thing. The probability that I start from x is somewhere in the middle, that I visit A before Z. Sorry, for you it's A before Z. Right, and the value, so I take one step I condition on the first step of the random walk, right? And then if I know that I went to this vertex, to one neighbor of x, then the new probability is just from this vertex, the probability that I visit A before Z. So this is an average on the first step of the same quantity on the neighbors. So this function is clearly harmonic at every point that is not A and Z. So h tilde is harmonic at v minus az. Right? What are the boundary values that it receives? 1 and 0, right? Because h tilde of A is 1. When I start at A, I obviously, with probability 1, visit A before Z, and at Z, I cannot visit A before Z because I'm already at Z. So H tilde of A is 1, H tilde of Z is 0. So how do I get any arbitrary values? An affine function, right? So if I take a harmonic function and multiply all the values by the number 5, I still get a harmonic function, right? Because the definition of harmonicity is a linear equation. And also, if I add to each value the number 3, then it still is a harmonic function, right? So I can multiply by multiplying h by some constant, right? So if I want the boundary values to be 5 and 8, and here I give you a function of the boundary values are 0 and 1, then I will multiply this function by 3, right, and add 5. Right? So this will give me that the difference between the two values is 3, and I'm pushing it to be 5 and 8. By multiplying by some constant and adding another one, and adding another, I can get any boundary values. Okay, so we proved, we discussed what is the harmonic function, and this should be very, very familiar to you. And what we're going to do tomorrow is look at the dual, the combinatorial dual object that is the harmonic function that describes to us what is a current, right? So perhaps in the 3 minutes, I'll just define this object. So we always have harmonic functions, which are functions on the vertices. And somehow a dual object is a function on the edges. But they have to be very special functions. So let's just say what is a general flow on the graph. And we'll discuss its properties later on. I will repeat this definition tomorrow. Right? So flows. Right? So a flow. So it's a function. It's a function on directed edges. So it's a function. Let's call it. What am I using here? Theta on directed edges of G. So even though G is not a directed graph, right? The function is going to be defined on directed edges. So I imagine that every edge appears in both orientation, and I just define the function to receive, will possibly receive a different value on the two orientations of the edge, but will always have the condition that it's anti-symmetric. So if I give the value 5 in this direction of the edge, then it will receive the value -5 on the other direction, right? So it's a function theta from E to R, and let's just state its properties and end with this. So one, it will be anti-symmetric. Theta of xy is minus theta of yx. Right? This is what we expect from an electric flow to have. And also a thing that we expect is that so we think about this function as telling you how electric flow or even water flow goes from A to Z, right? So if we have such a thing, if I have a network with A and Z and I put a liter of water in the beginning and it flows down to Z, then there's a liter of water that went through Z, a liter of water that went through A, a liter of water that went into Z, and all other vertices, whatever comes into them, must flow out of them. Right? So this is the condition that we want this function to satisfy, and I will write it this way. So for any vertex v that is not the beginning or ending, what comes out, the inward flow equals the outflow. So in one way of writing is if I sum over all the vertices w such that w is a neighbor of v, then theta of vw in this direction is 0. Right? So I think about a vertex v, and I look at the sum of all of these edges pointing outwards. So remember, so some of these values are negative, right? Meaning that flow is actually going inside, and some of these values are positive, which meaning that the water are going outside. And what we want is that the sum of all of these things is 0, right? And this means that exactly what the negative values match up exactly. Their sum is exactly the positive values. So what goes inside is what comes outside, right? So this is a flow, and it's in some sense dual to the voltage, and we'll see tomorrow what other properties an electric flow satisfies. Okay, so we'll continue tomorrow. Thank you.